And in this formula also, in place of b you can write d, provided this n is not equal to n plus plus, this n plus plus, because that is not in the domain of d. So d is a function whose domain is actually equal to the domain of an, that is the set of natural numbers starting from 0 and ending at n, and also it satisfies exactly the properties that we know to be true for an. So what is your conclusion now? D is a function that is just like an, but according to our induction hypothesis, an is a unique function which satisfies these properties for that particular capital N. So by the induction hypothesis, we have D is equal to an. So D and an are identical, and this is coming from uniqueness of an. You can mention that if you want. Because an is unique. Okay. So on this part of the domain, B matches with an, but according to our supposition, B and an plus plus are not equal. So if B already matches with, also note that, okay, so what I am trying to say, I think I am confusing you. You see, this domain can be written as a union of two sets. On this part of the domain, B and an plus plus are the same thing. They act identically. They have the same output for the same input, and that restriction function for B is D, and for an plus plus, if we take the restriction of an plus plus on this part of the domain, it is an. Okay, you can clearly see why it is an. You go back to the definition of an plus plus, there itself you can see. And these two are equal. So what about this non-equality or inequality? So that means B and an plus plus should be different at this point, which is the only point about which we don't know. That is why, so our supposition B not equal to an plus plus, then forces us to conclude that the value of B at n plus plus is not equal to the value of an plus plus at n plus plus. This is our conclusion. We are being forced to conclude this because of this supposition, but that is not true. Let us see why. But what about Bn plus plus? According to the formula that B is satisfying, according to our assumption, this is nothing but Fn B because that's what we assume B to satisfy. We don't know anything else about B, what its formula is, or like what we know about an plus plus in terms of an, that we don't know about B. We only know that B satisfies some relations, and this is one such relation. Okay. Now what about this n? This n belongs to the domain of D. So since D is the restriction of B to this set, so I can replace here B with D. But we have already seen that D is equal to an and n belongs to the domain of these functions. So this is equal to f of n comma an of n. Here we are using this equality. And if you now go back to the definition of an plus plus, you will see that at what I am trying to say. Yes. If we now go back to the definition of an plus plus, you will see that from the formula that we have written for this one in its definition, this is nothing but an plus plus n plus plus. So this directly contradicts this conclusion. This is a contradiction. And shows that our last supposition is wrong. Last supposition is wrong means we have assumed that a function B exists which satisfies those requisite properties and which is different from an plus plus. Such a function cannot exist. So an plus plus is unique. That is, an plus plus is unique. Okay, so this completes the current induction. It proves that if we have a unique function satisfying those properties for the integer n, I uttered the word integer, natural number n, then a unique function satisfying those properties also exists for the successor n plus plus. So this completes the induction. And proves that for any n which is a natural number, such a function an exists which satisfies some properties. Okay, so that is fine, there is nothing else about it. Now using these functions an, remember these functions are only given the hint. We actually have to prove that there is a function a from the set of natural numbers into the set of natural numbers satisfying some properties. That we are now going to define using these functions an, and that we will define like this. Now define a from n into n by this formula an n. You keep in mind what an is. This an is coming from this this part of the solution, the first part. Also, just for the sake of reminding you again, the domain of an is this set. So the fact that n belongs to the domain makes this formula well defined. So the value of a at n is defined to be equal to the value of an at n. And because of this way of defining a, clearly a is well defined because each an is well defined. Clearly a is well defined. Now we have to show that a satisfies those properties which actually are the things we want. Now, what is a of 0? According to this definition, a of 0 is nothing but a0 of 0, and this is again nothing but c from our previous result that we proved by induction. And a of n plus plus is equal to an plus plus n plus plus. This is equal to f of am I getting confused again? No. Okay, let me first write and then we will try to figure out what we have written. An plus plus n and this is equal to f of n n and this is equal to f of n comma a of n. What have we done here? Let us justify all the steps. This equals this, that is coming from the definition itself. Okay, in place of n plus plus, you will write it as a suffix. Now, what about this function an plus plus? An plus plus is a function from this into n such that 0 part we don't need, but we need this an plus plus I plus plus is equal to f of I comma an plus plus I for all I belonging to n such that I is strictly less than n plus plus. That's what this function satisfies, right? Besides that other relation that it has to be c at 0, besides that, this is the other thing it has to satisfy. Now, after this step, can I put I equal to n here? I can, because n is less than n plus plus. So in place of I can choose this value n. If I write here n in place of I get this. Here what I will have, f of n an plus plus n. Okay, so the second step is also justified. What about the third step? You see, just like this one, an is a function which has this as domain. So if I have one more thing that you know is this. I think I should have mentioned this. Before writing this paragraph, I should have mentioned this. What I mean by that is this. If I restrict this function to this set, then I actually get nothing but an. And this can also be proved by induction using the formula for an plus plus. Do I have to wrap this up? I have to. I have no other choice. Okay, we will again write but we have understood what we have written here. We don't have to justify it twice. The above paragraph shows that we perhaps also have this an plus plus restricted at this set is equal to an for all n belonging to n. Indeed, this is true, and can be easily proved by induction. Okay, we need this. I needed this here in this calculation, so that's why I have to mention it. Okay, let us keep it for now, and now we define that function. By a of n equal to an of n. Clearly a is well defined. Also, a of 0 is equal to a0 of 0 is equal to c. For any n belonging to n, we have a of n plus plus is equal to, by definition this is equal to an plus plus n plus plus. Okay, and here we have already seen we can, in place of this term, we can write f of n comma an plus plus n. That we have already justified while we were writing these relations before. Now we can use this one. You see, n is not only an element in the domain of an plus plus, but it's also an element in the domain of an, and in that domain an, if we restrict an plus plus, it becomes the function an. So n is in the domain of an, and the restriction of an plus plus on that domain is an. So in place of this I can write f of n comma an of n. Okay, so that is the justification for this step. And now if you again use this formula for our original function, then I get f of n, a of n. So our function a not only satisfies this first relation, it also satisfies the other thing, and this is true for any natural number n. Okay, so such a function that we want actually exists. Now we have to prove that this function is unique, this function a is unique. So for that we will now again same procedure, just like how we showed that an plus plus is unique. We considered a function b which we supposed to be not equal to an plus plus, still satisfying those properties, and then we arrived at a contradiction. So here we will assume a function, but we will not prove it by contradiction, but again by induction. Okay, so now we come to the question of uniqueness of A. Suppose there exists a function b like this, such that b of 0 is equal to c and b of n plus plus is equal to f of n comma b of n. For all n belonging to n, that is b satisfies exactly the same properties as a. We will now prove by induction that b and a have identical outputs at every natural number. Have we used b already somewhere in this solution? Oh, we used b, no? We have used b here. So let us denote it by something else. Let us denote it by e. Or we may confuse ourselves into thinking this b is that b. By induction, that a of n is equal to e of n for all n belonging to n. This will definitely prove that a and e as functions are equal, because already they have equal domains and equal ranges. Okay, so to start off, we have to calculate the values at 0. What is a of 0? A of 0 has to be equal to c, because it satisfies that property. And so does e. E of 0 is also equal to c. So at least at 0 they have identical value. Assume a of n is equal to e of n for some natural number n. So this is our induction hypothesis for the current induction. Then an plus plus. The an plus plus has to be equal to this, f of n comma a of n. But we know that a of n is equal to e of n. So this is equal to f of n comma e of n. And since e also satisfies this property, so this is equal to e of n plus plus. Recursively defined functions or recursively defined whatever is, if you want to prove something about such an object that has been recursively defined, induction is the easiest way to go forward. It's because of the fact that in a recursive definition you have a description of the nth stage based on the n minus 1th stage. So it's like it has been put in a fashion that it's the easiest to apply induction. So that's why you can see here it's almost straightforward. We have written it like this, it satisfies this property, but then an is equal to en and e also satisfies that property, so we get back this. This completes our current induction and proves that A is equal to E, that is A is unique. So this is the first part of the solution. We have proved what we wanted. There exists such a unique function that satisfies so and so properties. Now we come to the challenging part.